Hi everyone, and welcome to episode number 8. So today we're going to be talking about two specific implementations of oscillators, the Wien bridge oscillator and the Pierce oscillator. So what we're going to do is we're going to kind of split this up into two separate segments, but all in the same video, where the first part we're going to be at the whiteboard discussing the schematic for both oscillators, talk a little bit about the history, where it comes from, and the different parts that are necessary to implement them. And then in the later half, we're going to go to the breadboard, implement it, and see the oscillator in action. Now, if you're looking for general information on oscillators, I suggest you go take a look at the video that was released a couple weeks ago now by the Signal Path blog. It's a really excellent video where it shows off some of the different types of oscillator packages there are that you can get from DigiKey or whatever, and shows the resulting signal on like a spectrum analyzer, and it's very excellently well done. Go check it out if you're looking for some general oscillator knowledge. But here we're just going to be talking about these two specific implementations, and I think you'll see that the second one, the Pierce oscillator, is very applicable to pretty much everybody working with digital design. So before we get started with that though, I just wanted to take a couple seconds to talk about the progress on the USB to Gpib adapters. Pretty much all the parts are here now, which is great, including all the cardboard boxes. I'm going to need to, ship them to you guys. But the only thing that's not here yet are the Pcbs. It actually took me a little longer than anticipated to actually get them ordered. There was a lot of logistics that I had to go through. You know, I've been meaning to release the source files for these for weeks now. But as I mentioned in an earlier video, I said, might as well wait until I actually have them and ready to be sold before actually giving out all the source information. Just so that in case I've tweaked a few things here and there, I want it to be exactly the same, right? So I was like, okay, well, let's get these ordered and made and able to be sold. And then I was wading through all the stuff that then I had to do to be legally allowed to do some of these things, like sell them, right? So technically now I'm a business owner. So this is something that I've been wanting to do ever since I started my undergrad back in 2007. When I started in physics, I wanted to be able to, when I finished my undergrad, own my own business at some point. It's really what I wanted to do, but it wasn't until my 4th year that I discovered that I really love electronics, and that's what I would want my business to be. So now that I'm doing my master's and I attend a university where I get to keep all the intellectual property rights to everything that I create, I figured, hey, it's as good of a time as any. Might as well get this done. So I'll release some more information about that in the next coming days. But everything's going really well. Board should show up next week, and you guys will see an update on that in a little bit. All right, let's get to the board now and take a look at these oscillators. So first we're going to talk about the Wien bridge oscillator. Now, before we start, I'd like to point out that I don't actually know if that's how you pronounce it, but So it's based on the bridge circuit by Max Wien, who came up with that bridge circuit in 1891. You can look up that circuit on Wikipedia if you're interested. And what we've got here is actually the modern version of William Hewlett's 1939 Stanford University master's degree thesis, where he implemented this. Now, obviously back then they didn't have op-amps, so his implementation would have had, tubes or whatnot. But again, this is the modernized version, and you can find the schematic on Wikipedia. So if we just kind of go over a little bit here, he's got, so this is the actual bridge circuit part, and here we've got some gain control to actually make it oscillate. If you don't have, you're supposed to have unity gain for an oscillator, but if you don't have enough gain at startup, it'll never actually start oscillating because the zero state is well, the zero output state is stable. So you need to have a little bit of extra gain at the beginning, and then that gain needs to be reduced later on. So what we've got here is this is what Mr. Hewlett actually did a really cool job of, is that this is his way of introducing amplitude stability. This is a lamp. This really was a lamp that he had, like a light bulb, inside his oscillator circuit. And the great thing about it is that as more current goes through the lamp, through the filament, the resistance of it increases. So at startup, it'll be low. So the gain of this circuit, right, is going to be very high. So then it starts up. But then as current flows through, right, that's going to heat up and decrease the gain of the oscillator. Because now you don't need all that gain anymore. Now you want a proper oscillator to continue to function. So you want to decrease the gain. So this was his way of introducing amplitude stability, which was actually a really neat idea. So of course, for an oscillator, you have to have some positive feedback going on here. So, ta-da! And if we set R1 and R2 to be the same, and C1 and C2 to be the same, we get a nice equation for the frequency at which it's going to oscillate at. Well, there you go, 1 over 2 pi RC. And of course, ideally, this feedback resistor here is supposed to be equal to 1/2, or no, this is supposed to be 1/2 of this when this is fully warmed up. Something like that. You can look it up on Wikipedia, but I don't think any of you guys are actually going to build this oscillator with a lamp in it, especially nowadays with light bulbs being, of course, substantially different than they were back then, and blah blah blah. So this was you can modify this circuit a little bit, right? Let's say you put just a regular resistor there though for your gain instead of a lamp. Well, now unfortunately you don't have that amplitude control anymore, so you're not going to get a very nice oscillator. So if you look at the Analog Devices application note 580, you get a circuit that looks like this. So you've got your caps. This is your so they have it upside down compared to that one, right? So again, notice that the terminals have been switched there. So there's the capacitor, resistor, right, ground, and of course these are actually pots. Right, and this is 2.2 nano, 10K, 10K, 2.2 nano. Right, so we've set the two pots to be, the two resistors to be the same, the two capacitors to be the same, and when you adjust these, you need to adjust them both together. That's the idea behind it. So here's the part, of course, where we don't have the lamp anymore. So what we're going to do instead is we're going to put a constant resistor there to ground to define a constant gain, right? So this is, whoops, just dropped the cap, 2.1K, and this is 1K, okay? But now we're going to add in here, we're going to add in a resistor that's tunable, so we can adjust the gain. So another pot, and this one's 100K. And here we're going to put two back-to-back diodes, two cross diodes there, like so. So that's what you'd find if you look in the, again, the Analog Devices application note 580. So this produces the same sort of effect. It gives you that amplitude control that you're going to need to get a nice oscillator out of this. And this is what we're going to build up. Now, that said, I don't actually have pots that are 10K or 100K. So what we're going to do instead is we'll end up just using fixed resistors for those, and we'll just change them to see how the frequency changes. And here we'll use like 47K with one of my 50K pots in series. You know, like it'll be close enough for just to see what's going on. So we won't be able to reproduce it exactly, but hey, it'll still be pretty cool. But first, let's take a look at the Pierce oscillator and why that is actually more exciting in some ways than this one. So here we've got the Pierce oscillator, and of course, it was named after its inventor, George Pierce, and this is the circuit that is used by virtually all digital IC clock oscillators. They're basically all Pierce types. You know, I'm sure you'll notice that if we separate this part right here, and you just look at that, that's pretty much what you end up connecting to your microcontroller. You know, you put your crystal between the two pins, and then you make sure you put your two capacitors going to ground attached to each of those pins also. All the rest of it is internal to your microcontroller. Now, you don't always have that luxury of having the rest of the parts. So sometimes you still want to use your crystal to generate some sort of clock. So why not actually just build it up, right? So what we've got is we've got an inverter, we've got a feedback resistor, and we've got the crystal and these two loading capacitors here. So the inverter with this feedback resistor puts the so if we didn't have anything else attached to it, right? So we got rid of the crystal and the capacitors and everything. It's just the feedback resistor and the inverter. The output of the inverter will be mid-supply because, of course, the inverter wants to output the opposite of the input, but because it's connected to itself, it can't do that, right? So basically, we're setting the inverter to be where where it actually has some gain. And this down here, the crystal, it acts as a highly selective filter element. So what we're going to do is basically just allow the frequency at which it's supposed to oscillate at to actually, well, propagate through. So it's considerably simpler than the previous one because, well, you've got only just a couple elements. You don't actually have to tune them to be a certain frequency. You already have this crystal which has been built and designed for a certain frequency, and then you just put in the rest of the components. Now, of course, if you're doing this for a microcontroller, right, and this is all internal, right, because we're assuming micro for a second here, and when you buy the crystal goes on the data sheet that it needs some load capacitance. These are your load capacitors here. So if you look on Wikipedia, not only is there a derivation for how this whole thing works, and I don't want to get into that because it's just a whole bunch of math. There's an equation that'll show you what the actual load capacitance is because you have to take into account the straight capacitance from your PCB or your breadboard, the straight capacitance from the leads on your crystal, the input capacitance from your microcontroller. You gotta include all those factors in. So if the crystal says I need 18 picofarads for my load capacitance, you can't just put 18 for your capacitors there. You need to actually do a little bit of math and see what the optimal value is. Now that said, if you put in a value that's not optimal for C1 and C2, it's not that big of a deal because it's still going to work. It just won't be exact. You can, if you actually match the load capacitance to what the datasheet says, you'll get the most accurate reproduction of the frequency that it's supposed to oscillate at. So if you don't put the right ones there, you will not be within spec. So another thing that is usually added is another resistor in here And you can look that up on the internet. It adds for additional stability or something like that, but not a big deal. But before we continue on, another thing that you can think about when analyzing this is that this is kind of like a pi network here. You've got your two shunt capacitors, and you've got basically some sort of inductive element there. And well, a pi network of an inductor and two capacitors is going to resonate at some frequency. And you can look that up, and it's pretty straightforward and pretty simple. But we're not going to be talking about that. So this we will also take a look at, and I hope that my inverters that I have, which are a little bit old, but should still work, are able to go fast enough for the crystals that I have. So let's head on over to the breadboard and see how both of these oscillator types work in action. Alright, so I've gone ahead and breadboarded up the Wien bridge oscillator, and I had to change a couple of things, right? You know, I don't have 10K pots, so I just put straight up 10K resistors in, and I put in instead of a 100K pot, I put in 47K in series with a 50K pot, and I figured that would be close enough. And I've already tested this to make sure that it works, and it does, so we're all good. Now, I'm going to go ahead and turn on the power for it, but I hope that the fan from the power supply doesn't get picked up too much, because I'm using my crappy desktop power supply that I've kind of converted. So if we go ahead and turn that on, and I come over here, and we take a look, I've already kind of adjusted it so that it ends up looking nice. And what you get is you get a decent square wave. Sine wave, I'm sorry. And according to the oscilloscope there, it's running at about 7.7, 7.8 kilohertz. So if I adjust that potentiometer that I have, you'll see that the amplitude changes, right? Because this is our amplitude stability control. The gain is, 2.2K, and then the feedback resistor is 2.2K with a 1K resistor, right? So it's going to be 1 plus 2.2, so 3.2 gain. But of course we've got that those back-to-back those diodes there with the potentiometer, right, to ever so slightly adjust the amount of gain, and you need that in order for it to be stable. So if I put my hand on it, you can also see that you get a lot of noise from myself introducing it there. So if I let go of the pot, it looks pretty good. So now to show you what it looks like if we introduce a lot of gain, so if I remove that completely, this is what you end up getting. This is it now peaking out the power supply there, because we're on 2 volts per div vertical, and we're on a plus minus 5 supply here, so we've got 10 volts of swing. So that's with it, without it. See, that's why you need that. Even if it is just affecting the gain just a little bit, that little bit is still necessary to make it look all right. So ideally you would then take this, buffer it, and you'd probably want to still filter it, but pretty good. So if I just bypass that completely, and I'm just using the pot, right, you can see we've got quite the range. This is only a 1-turn pot, right? So this is it's pretty neat, isn't it? So there you go. That's what you get with a Wien bridge oscillator. It works in a pinch, and if I had some more adjustable resistors there, we'd be able to see how the frequency changes also when we adjust the other resistors. According to the application note, this specific design with these capacitors goes up to somewhere in the neighborhood of 100 kilohertz if you put 1K resistors instead of the 10K. So I'll put those in, and why don't we take a look what that looks like. Alright, so I've gone ahead and replaced those 10K resistors with 1K, and we'll take a look at what the scope looks like. So here we go. So I haven't changed the horizontal time base there, and we still actually have that 47K resistor bypassed. I haven't changed it yet, so it's only the potentiometer that's helping tune the gain. So we zoom in a little bit, and if we just play with the pot and don't actually reintroduce that one, you can actually get it pretty decent just with that alone, but it's really finicky, of course, because all of a sudden you're going to cut out nearly all the gain. So let's re-include that back in, just so we get some finer control. And of course, if you had a 10-turn pot, this would be considerably better. But that looks pretty good, and that's running at what? Just shy of 80 kilohertz there, according to the scope. We can make it a little better. Oh, beautiful. So there you have it. It's actually a pretty versatile circuit there. So if you wanted to, you could also put in digital potentiometers instead of analog ones, and then you could make sure that the, of course, you'd have to calibrate it with some actual analog like trim pots, because digital pots, they have quite the percent tolerance there from one to the next. It's a couple percent. I feel like it's like 3 or something percent. Let me turn off the power supply. So you can put in digital pots. You can make this digitally controlled if you wanted to adjust the frequency, and yeah, that'd be kind of cool. Of course, again, you'd have to calibrate them so that both the resistors would have to be the same. So you'd put in a small trim pot to be able to match the like a slight offset that one pot has to the next. But that'd be pretty cool. Anyways, let's take a look at the other oscillator, the Pierce oscillator. So I'll breadboard that up and we'll see what it looks like. Alright, so I've gone ahead and set up the Pierce oscillator here. And what we're using is just a hex inverter. It's a little bit of an older chip, this one specifically, and thus doesn't run at very high frequencies. I'm already kind of pushing it to its limits here with this particular crystal. If you're interested, it's the 4000 CMOS series. It's the 4069, right? But just this specific one is pushing it a little bit in terms of specs. So what we've got is just a 20 megahertz crystal, and I grabbed some close enough capacitors here. I know I didn't. It's just whatever I had kind of conveniently nearby, and these are both 22 picofarads. And what we're going to do is we're going to look at the output, and our feedback resistor here is a 1 mega ohm resistor. So if you're looking online, most of the time they'll suggest 10 mega ohms, but I actually don't have any around, so we're going to go with the 1 meg. I'm also not using that series resistor that we didn't talk about, but I did mention when we were at the whiteboard. That's not being used in this. Usually you'd use something around maybe 2K or so. But we'll still be able to see what's going on in the scope. So also, the other change that I've made is that we're not using, of course, dual supply anymore. We're just using the 5 volts and the ground. So let's take a look at the oscilloscope. Alright, so I haven't turned on the power supply yet, but do note that this is AC coupled, so I just changed it just so that you can see it a little bit better. Alright, so there we go. So we've got a decent enough looking sine wave, and according to the oscilloscope, the frequency is 20 megahertz, plus or minus quite a bit. Now, there's going to be a lot of error because we're not using, spec'd components here. We're not using the appropriate capacitor values. We haven't calculated all the required actual capacitors, taking into account the stray capacitances from the breadboard and whatnot. We're also not using that series resistor that we talked about, and again, we're only using 1 meg instead of 10 meg. So you're going to get a lot of little fluctuations that you might be able to see on the scope here. So if you take a look, it's kind of waving about there a little bit, but It's close enough. So if you were to take this now and you were to plug this into another inverter, you'd get a nice square wave, which you can use for clocking various components on your board that don't have these parts internal to them. So, for example, a DDS chip will not have the internal parts to actually generate the clock. It'll just expect you to give it a square wave into its master clock port. So you'll have to either get an oscillator, one that's already got all the parts required and just outputs a square wave, some sort of temperature controlled or oven controlled oscillator, for example. Or grab one of your crystals that you've got, set it up with an inverter, and see what happens. All right, that's about it for these oscillators. Well, that about does it for today's episode. If you're looking for more information on Pierce oscillators, be sure to check out Fairchild Semiconductor's application note 340. So, I'll have some more details in the next couple of days for my exciting new business, which I'm totally excited about also, in case you didn't notice. But not for this episode here. I'll try to keep them at least a little bit separate. So if you've managed to make it all the way to the end of my video here and managed to survive me blabbering on at times about seemingly nothing important whatsoever, I want you guys to leave a comment below and use the word oscillator somewhere in your comment. If you use the word oscillator, it'll let me know that you made it all the way to the very end, and it makes me feel good about myself and that people are actually watching my videos. So, yeah, thanks for watching, guys, and I'll talk to you next time. Bye.